Hello there, this is an Algebra 2 video. It is Chapter 7, Section 4, and today we are going to be solving logarithmic equations and inequalities. A couple sections ago we learned how to solve exponential equations and inequalities, and now we are going to be dealing with the inverse of the exponential, which are logarithmic, and solving logarithmic equations and inequalities. And so you recall from the previous lesson that the easiest way to do this is to basically be able to transform from logarithmic form to exponential form. That's the easiest way, in my opinion, to do it. It's not the only way. And so to solve this first example, we can use our little circular chart thing that I tried to show you in the last section. And so basically what this comes down to is if I transform this into exponential form, it's going to read 36 to the 3/2 power equals x. And then it doesn't seem so daunting to solve for x. So we know that 36 is actually the same thing as 6 squared. So really we have 6 squared to the 3/2 power. And the reason why I did that is because we have a rule or a property that says when you have a power raised to a power, you can multiply the exponents. So basically I need to figure out what 2 times 3/2 is. And that's going to be nice and easy because the 2's are going to cancel and you're just going to get 3. So at the end of the day, you're going to get 6 cubed equals x. And 6 times 6 is 36. And 36 times 1 more 6 is 216. So it turns out that x equals 216. And that is your answer for example 1. So now I will let you try these two little guys. Remember to try to put it in exponential form first. It'll make it a lot easier for you as you're solving. And then we're going to try another application. And in this case, the difference is that you have log on both sides. I want you to notice that they have the same base. They're both log base 2. So the only way for two logarithms that have the same base to be equal to each other, which is what they're saying here, is for this portion of the logarithm to actually be equal to each other. So basically what this is telling me is that the only way for these two logarithms to be equal is for x squared minus 4 to equal 3x. If I can figure out when x squared minus 4 equals 3x, and provided that those solutions are within the domain of the logarithm, then I have my answers. So x squared minus 4 equals 3x is actually a quadratic that we learned how to solve a long time ago. So we're going to make this into an equal to 0 situation. So we're going to move the 3x to the other side. And then we're going to get x squared minus 3x minus 4 equals 0, which is probably very factorable. Factors of 4 are going to be, let's see, what do we want to do here? 1 and 2, let's try that. If, no, let's try 4 and 1. Let's do 4 and 1 like this. And we're probably going to want to make this a negative 4. Let's try that. So you're going to get negative 4 this direction and positive 1 this direction. And negative 4 plus 1 is in fact negative 3. So it checks with that. And 1 times negative 4 is negative 4. So we're good to go. So it factors out to x plus 1 and x minus 4. So my two solutions are negative 1 and positive 4. Or I should say my two potential solutions are negative 1 and positive 4. But you still need to check those solutions in the original to make sure that it's in the domain. For example, if I plug x into the 3x here, if I plug negative 1 into this x, I'm going to get log base 2 of negative 3. And we cannot take the log of a negative number. It's not in the domain. So that means that negative 1 is out. It's an extraneous solution. But what about 4? If I plug 4 into here, 3 times 4 is going to be 12, and that's going to be a positive number, no problem there. And here, if I plug in a 4, I'm going to get 4 squared, which is 16, and 16 minus 4 is going to give you 12, and that's not going to be a problem either. So my final answer is that x equals 4. You don't want to include the negative 1 because it was an extraneous solution. So it's very important in these examples that you, or in these problems, that you actually check your solutions. Okay, so here's your do-it-yourself question. Don't forget to check your solutions at the end. And then we're going to go into the inequality scenario. And with inequality, it's a little bit trickier. Especially if you're going to be using the diagram that I've been showing you, okay? Because we know that it's going to be 3 to the 4th and x, but this is not an equal to. So is 3 to the 4th greater than x, less than x? How do I do that? And that's kind of what I put this up here for you for. It says if the base is greater than 1, which in this case it is, 3 is greater than 1, and if the x value is greater than 0, then log base b of x greater than y, which is basically log base b of x greater than y, in this case y is 4, then that means that b to the y is less than x. So we have our b to the y less than x, which is basically the same thing as saying x is greater than b to the y. So these two are the same thing. But if we do that, I just wanted to be clear that I showed that to you because you might have noticed this is a greater than symbol here, but it kind of looks like it changed to a less than symbol. That's because it's written backwards. If you put the x on this side, then it would say x is greater than 3 to the 4th, and it would be consistent. But I like to do my little diagram, so for me it's easier to do it this way. But if it confuses you, you can do it the other way as well. So 3 to the 4th power is actually 81. So 81 is less than x, or you could say that x is greater than 81. And that would be your solution for that little guy. So now, we'll let you do these two. And then we're going to go to our last example, which is similar to the one that we did with the equations. You're going to have log on both sides of the inequality symbol. And just like with the equation scenario, the only way for this logarithm to be larger than this logarithm is for the x plus 3 to be larger than the 2x plus 1. And if for some reason this had been a less than, it would still be the same thing. The only way for this logarithm to be less than this logarithm is for the x plus 3 to be less than the 2x plus 1. So what we really have here is x plus 3 in this case has to be greater than 2x plus 1 in order for these two logarithms, this inequality to maintain its symbol here. Again, make sure that they both have the same base. So they do, they both have base 4. So x plus 3 has to be greater than 2x plus 1, and of course, check your solutions at the end. So I am going to subtract x and subtract 1. So 3 minus 1 is 2, and 2 minus 1 is x. So I get 2 is greater than x, or the same thing as x is less than 2. So the other part of this situation here is that you're not done just yet. You might be thinking, oh, x is less than 2, yay. But no, if you plug 2 into this, 2 plus 3 is 5, that's not a problem. 2 times 2 is 4, is 5, it's not going to be a problem. They're going to be equivalent there. But the problem is that we have domain issues for logarithms. Okay, so the log can never be negative. So in addition to it being less than 2, you have to figure out when is x plus 3 negative, when is x plus 3 less than 0, and also when is 2x plus 1 negative, or when is 2x plus 1 less than 0. So you basically have 3 separate inequalities going on. You have the first one that kind of gives you the x is less than 2 part, but now you got to figure out the domain. So subtract 3, so x is less than negative 3. And then over here you want to subtract 1, and then divide by 2, so x is less than negative 1/2. So now you got to figure out on your number line, so I'm going to draw myself a number line here. I'm just going to try to show you how this works. We want to put all these numbers 2, negative 3, and negative 1/2 on our number line. So here's negative 3, and here's negative 1/2, and then you have a 0 somewhere. And then you have 2. Okay, I'll have to put the 0 in there, right? So we know that we have to be less than 2. So that's going to be this direction, less than 2. We know we have to be less than negative 3, but we're already less than negative 3. Because if you're less than 2, then you're automatically going to be less than negative 3. But we have to be less than negative 1/2 as well. So, or we have to avoid those scenarios, I should say. So really what we should be saying here, I just made a little boo-boo. Well, it's not a boo-boo, but it probably would have been easier I said over here earlier that we wanted to know when it was negative. So x plus 3 is negative when x is less than negative 3. So really what we want to say is we want it to be positive because we don't want negative numbers, we want positive numbers. So there's two ways of looking at it. You can either avoid all the things that can't be, or you can just say what can be. So let's be optimistic and say what can be. This is the pessimistic way of looking at it. This is what it can't be. But what it can be is positive. So if we make that a positive, then x can be greater than negative 3. So we want this to be greater than negative 3. And then this guy, same thing, we want to change this to a greater than. So we can talk about what it can be as opposed to what it can't be. And x can be greater than negative 1/2. So here's greater than negative 1/2. So see, you'll start to see that as long as you are between negative 3 and 2, you're okay. So our final answer will be that x has to be less than 2, but greater than negative 3. And you end up with this sandwich of a solution for example 4. So there you go. Now we are going to let you try this little guy. Don't forget to check your solutions and to make sure that you also check for the domain of these two guys as well. Alrighty, and once you've completed that example, then you will have completed your notes for this lesson, and I will see you in class, and thank you for watching.